that we can start. So on Monday, we started chapter 3, which is about parametric point estimation, and we discussed what is parametric point estimation. So for the benefit of those who were not with us on Monday, so we have a population. We discussed what is the statistical inference. So I'm not going there, but you know by now what we are dealing with or what we are doing in this module. So we have a population X following the density function f of x with theta being the parameter. So we want to use the sample data to estimate the value of theta. So we want to use the sample data to estimate the value of theta, which is the target parameter. So we spoke about the methods that we can use to find the function that we can use, or a statistic that we can use to estimate theta. So we must have a statistic so that when when we have the sample data, we are able to estimate the parameter, which is theta. And we said before estimating theta, now we have to define a set of acceptable values of theta. And that set is called the parameter space. So we looked at the definition of what is a parameter space, and it's nothing but a set of acceptable values of the target parameter. Then we looked at those two examples. Then now we defined an estimator, which is a statistic that can be used to estimate the target parameter. And we looked at these 4 methods that can be used to find this estimator. So estimator of theta is nothing but a statistic. We have been discussing statistics in chapter 2. So on this chapter, we are looking at a statistic that we can use to estimate the population parameter. And we discussed the first method, which is the method of moments. We discussed the first method, which is the method of moments. And the basic principle of this method is to choose the value of the unknown parameter for which the sample or the observed data has the same moments as the population, because we have the population moment, we equate that to the sample moment, and we solve for the parameter. So the basic principle here is to choose the value of the parameter, is to choose the value of the parameter from the parameter space. Remember, we have the parameter space that the value of the parameter should be within these regions or this set. So the method of moments helps us to choose the value from that parameter space for which the sample data or the observed data has the same moments as the population. That's why we equate the population moments to the sample moment, and we solve for the parameter. And we looked at those 3 examples. So today we are here, which is another method of finding the estimator. And this is called the maximum likelihood estimators, or the method of maximum likelihood estimators. So this method says if we have n independent and identically distributed random variables from the population X, And this population X is distributed with this density function. So we have an independent random sample from population X. And our population X is distributed with this function. So these variables are distributed with that function because they are from a population which is distributed with this, and they are identical. So they are all distributed with this. And the theta there is the target parameter, is the unknown parameter. So we want to find a statistic that we can use to estimate this parameter. So the likelihood function is the distribution, is the joint distribution function of these n independent random variables. So the likelihood function, L of theta, is nothing but the joint density function of these random variables. Let's go to the journal. I try to explain this. So what's happening is that we have a population X following this probability distribution function. So we take a sample from the population of size n. Remember, the aim is to estimate theta. The aim is to estimate theta. So now we want the likelihood function, and that definition says the likelihood function is nothing but the joint function or the joint functions of these random variables. So the joint function of these variables is nothing but f of x1, x2 to xn, and the parameter is theta. And we know that these variables are independent. So if these variables are independent, then the joint function is nothing but the product of these functions, because these variables are independent. So the joint function is given by the product of these random variables, and this is nothing. So we can just use the product of f of xi theta. So this is the likelihood function. So the likelihood function is nothing but the joint function. So it's the product of the marginals. Is it clear?
Yes.
Thank you. So now, remember, the aim is to find the function of, is to find the function that we can use to estimate theta. So the parameter, or the value of the parameter that maximizes the likelihood function, is called the maximum likelihood estimator of theta. So a statistic, or a value of statistic that maximizes this likelihood function, is called the maximum likelihood estimator, and is denoted by theta hat to indicate that is the estimator. So theta is the parameter, then theta hat is the estimator of the parameter theta. So what is this theta hat? So this tells us that the theta hat, remember, we have the parameter space, which is a set of the acceptable values of theta. So the method of the maximum likelihood gives us a value from the set, gives us the upper bound from the set, because this says theta, when using the method of the maximum likelihood, theta hat is nothing but the likelihood function in this set. And this set is nothing but the parameter space. So is the parameter space. So the supremum of that function in the parameter space, which is nothing but the smallest upper bound in the set. So our theta hat, it's nothing but the smallest upper bound. What's that? Yes. So our theta hat is nothing but the smallest upper bound in the parameter space. So the method of moments gives us that, gives us the smallest upper bound in the parameter space. Cell B, I'm saying the parameter space is the set of the acceptable values of theta. Remember, we want to estimate theta, or we want to estimate the parameter, which is theta in this case. So we want to find the value of theta using the sample data. So we have a set of acceptable values, and that set is called the parameter space. So that definition now says the maximum likelihood, or the method of the maximum likelihood, gives us theta hat, which is the estimator. And that estimator gives us the smallest upper bound in the parameter space. So the value that we get when we use the method of the maximum likelihood is the smallest upper bound in the parameter space. Are you answered? Now, the question now is, how do we then now find this smallest upper bound? How do we find the smallest upper bound? So this method, like I was saying, that this method, so inside the set, we have a set of acceptable values. So this method gives us the smallest upper bound, and this is how we get that value. This is how we get the value. So we have the 5 steps here. And the first one says we have to get a sample, because we have a population following a certain probability distribution function. So we have to get a sample so that we can use that sample to estimate. Now we have the sample. What we need is the statistic, is the formula or the function that we can use to estimate the target parameter. So the second point says define the function of the sample by the joint function. So we get a sample. After getting the sample, we define, or we get the likelihood function. When we have the likelihood function, we find the expression that maximizes the likelihood function. So this expression now is the statistic. So after defining the likelihood function, we have to find, using the likelihood function, we have to find the expression that maximizes that likelihood function. So this can be done by differentiating the likelihood function, and we equate the result to 0 and solve for theta. So this expression can be found if you have downloaded the guide. You will see there's a definition which says, or no, it's fine, I don't have to go to the guide. So after the definition of the likelihood function, there is another definition there. So that definition addresses the point that I'm making now. that to find the expression that maximizes the likelihood function, we differentiate the likelihood function, we equate the results to 0, and we solve for theta. Or we can do this. We can take the natural logarithm of the likelihood function, because the function that maximizes the log likelihood, the log, which is the natural logarithm of the likelihood function, is the same function as the one that maximizes the likelihood function. So instead of working with the likelihood function, we can take the natural logarithm of the likelihood function, and we differentiate that, we equate it to 0, and solve for theta. Then when we have theta, like we did with the method of moments, when we have theta, then we replace theta by theta hat to indicate that we are having a statistic or an estimator, not the parameter itself. So it must be clear that we are estimating the parameter. So we replace theta by theta hat. Then if we have the data, we can substitute into the statistic or the estimator, and we get the estimate. And we agreed that we defined an estimate as the value of the estimator. Is it clear? Is it clear?
Yes.
Yes.
Thank you. So let's now look at the first example. Let's look at the first example. So we have a random sample. We have a random sample, which is nothing but a set of independent and identically distributed random variables. So these variables are identically distributed with this probability density function. And the question is, what is the maximum likelihood estimator of theta? What is the maximum likelihood estimator of theta? So we have our function f of x theta, which is 0 otherwise. Then we have 1 minus theta, x to the power minus theta, x is between 0 and 1. So now, that definition or the statement said we should first get our sample. So we have our sample of size n. When we have the sample, and this sample is distributed with this function, now we can use this function to find the joint function, because these variables are independent. So the product of these marginal functions gives us the joint function. So we are going to find the joint function, which is the likelihood function. So we are going to find x1, x2 to xn of theta. So that is the joint function. And this joint function is nothing but the product of these functions. So it's x2 theta up to f of xn theta. And this is nothing but the product of f of xi. Sorry, let me correct this. It's not j, but should be I. So this is f of xi with the parameter theta. And now we have our f of x. Sorry about that. We have our f of x, which is equal to 1 minus. So we have 1 minus theta xi to the power minus theta. And now we are multiplying this n times. We are multiplying this n times. So this is going to be 1 minus theta to the power n, because we are multiplying this constant n times. So it's the constant to the power n. And this one will be the product of xi to the power theta. Now, let's go to this definition. We have our likelihood function. We have our likelihood function, which is 1 minus theta to the power n multiplied by the product of xi to the power minus theta. What we want now is the expression that maximizes the likelihood function. So I said to find this expression, we differentiate the likelihood function. We equate the result to 0 and solve for theta. Or we take the natural logarithm of the likelihood function, which is the ln of the likelihood function. So we take the natural logarithm of the likelihood function, we differentiate the natural logarithm of the joint function, we equate that to 0, and we solve for theta. So we are at that stage now. So we can differentiate this, or we take the log and differentiate the log. So if you are good with differentiation, then you can differentiate from this point. You can differentiate from this point, or you take the log, which is the natural logarithm of the likelihood function, and that log will be the log of 1 minus theta to the power n, the product of xi to the power minus infinity. I mean, to the power minus theta, sorry. Yes, someone's mic is on. If you want to say something, feel free. I cannot see the hand, if there's a hand up, because I'm working on this board. So now, the log of AB, it's nothing but the log of A plus the log of B. So I'm going to apply, or we are going to apply this to that. So what we are having now, this is our A, this is our B. Let me get a different color. So this is our A, and this is our B. So the log of that is nothing but the log of 1 minus theta to the power n plus the log of the product to the power minus theta to the power minus theta to the power minus theta. Again, the log of x to the power n, the log x to the power n, it's nothing but, so I will just write it here. The log of x to the power n, it's n log of x. So I'm going to apply that to this. So here we'll have n, the log of 1 minus theta. So what we're having here, let me get a different color. What we are having here, it's nothing but this, but n times, because we have the product of xi to the power theta, and I is ranging from 1 to n. So what we are having here is nothing but this. So we are going to have the log of x1 to the power minus theta plus the log of x2 to the power minus theta up to the log of xn to the power minus theta. And that is nothing but the summation of the log of xi to the power minus theta. So this expression here, it's equal to the summation. So this is equal to the summation of the log of xi minus theta, and I on the summation is ranging from 1 to n. Is it clear?
Yes,
Are
sir.
you guys following? Thank you. So again, I'm going to apply what I have applied here on this one. As you can see, we have the log of x to the power minus theta. So we are going to have n, the log of 1 minus theta, plus, so I apply this to that, we have summation minus theta, the log of xi, the log of xi. And this is equal to n, the log of 1 minus theta. Now we take minus theta out, so it's negative or positive. That will be negative summation, negative theta, because it's a constant, summation I ranging from 1 to n of the log of xi. So now we have the natural logarithm of the likelihood function. So as I've indicated, that it's either you differentiate the likelihood function or the natural logarithm of the likelihood function. So now we have the natural logarithm of the likelihood function, and we can differentiate that. So if we differentiate with respect to theta, the natural logarithm, which is the log of the likelihood function, we have, so n is a constant multiplied by a function of theta. So we are differentiating with respect to theta. So you know, when we differentiate the log of x, so with respect to x, this is nothing but x, and then you differentiate the denominator, and x in this case is going to be 1. So we are going to apply this here when we differentiate. So we'll have our n there as a constant. Now we have 1 minus theta. And when we differentiate 1 minus theta with respect to theta, 1 is a constant. So when we differentiate, that is 0. We differentiate minus theta with respect to theta, we get minus 1. So we have minus 1. Then we differentiate here, we have minus theta multiplied by this comrade. So this comrade, as you can see, it's a constant. So you differentiate minus theta with respect to theta, we get minus 1. So we'll have minus 1 multiplied by this guy here. So I is ranging from 1 to n. And that definition says, or said, that we equate the natural logarithm to 0, and we solve for theta. So we equate this natural logarithm of the likelihood function to 0, and this implies that minus n, so I multiplied this n with minus 1 there, minus n over 1 minus theta minus summation of xi log of xi, it's equal to 0. So that's what we are having. So since we want theta to be subject of the formula, we can take the minus summation to the right. And when we do that, the negative sign becomes positive. So what we are having now, it's minus n over 1 minus theta, which is equal to the summation of xi to the power n log of xi. Now, we want theta to be subject of the formula. So we multiply both sides by 1 minus theta. And when we multiply both sides by 1 minus theta, we have minus n, which is equal to 1 minus theta, summation of the log of xi, I ranging from 1 to n. Are you still following?
Yes, sir.
Thank you. And this is minus n. Now we multiply through by the summation of log xi to get rid of these brackets. So this will give us, because we're multiplying the log or the summation of the log with 1, we get that. We multiply again the summation of the log with theta. So we'll have theta, the log of xi. So we can take this to the left and we take this one to the right so that we can make theta subject of the formula. And when we do that, theta now, or this expression now changes the sign because it's going to the right. So we are having theta multiplied by the summation of the log. And the minus n, when it goes to the right, also changes the sign. So we have n plus the summation of the log of xi. And I is ranging from 1 to n. So you divide both sides by this expression so that we can have theta as the subject of the formula. So when we do that, we have theta, which is equal to n over summation of the log of xi plus summation of the log of xi divided by the summation of the log of xi. And this gives us n over the summation of the log of xi plus, this is 1 as you can see, plus 1. And this is our expression that maximizes the likelihood function. But the fifth step says we have to replace theta by theta hat to indicate that this is an estimator. So we have, therefore, our theta hat is nothing but 1. So I'm rearranging, I'm starting with 1 plus 1 over the summation I ranging from 1 to n of the log of xi. So this is our smallest upper bound in the parameter space. This is the estimator of the parameter theta. So if we have the data, we can substitute here and find the summation of the log of xi, and then we'll get an estimate, which will be the value of the estimator. Is it clear? Are you there?
Yes, sir. You are still here,
Yes.
sir. On my side, it's clear, sir.
Yes, sir.
Thank you.
Sir, can we please try the other method?
Sorry?
Can we please try the second method, whereby we don't involve the logs, we just differentiate from the beginning?
No, you can do that, ma'am. We don't have time, so you can do that. It's the method of differentiation. That's why I said if you're good with differentiating, because we have to get the the laws or the rules of maths, when you want to integrate, to differentiate, for example, how do we differentiate x to the power minus theta with respect to theta, where theta is the power? How do you integrate that? So I will have to go and first find that. So, and now I will be moving from teaching stats now going to maths. You understand? So I took this one because it's the simplest one. I don't want to spend the whole day trying to find out how to differentiate this, because from this it's easy to differentiate this one, but how about this? Because we have to differentiate that with respect to theta. So now I have to go to the rules of differentiations and check how do we differentiate this. So you can do that if you have time. You can just check this. How do you differentiate that function? And then you solve it. It will give you the same answer, because the expression that maximizes the log of the likelihood function is the same expression as the one that minimizes the likelihood function. Are you answered, ma'am?
Yes, sir. Thank you.
Thank you. So let's go back to the notes. So we have the second example, where we have a population which is normally distributed. We take a random sample of size n from that normally distributed population, and now we want to find the estimators of the population parameters mu and sigma squared. So that definition says we have to first get the joint function. So we have x, which is normally distributed with parameters mu and sigma squared. So the distribution of x is 1 minus, sorry, it's not 1 minus, but it's 2 pi sigma squared to the power minus 1 over 2 e to the power 1 over 2 sigma squared x minus mu. So now we have a random sample of size n distributed with the same distribution function, and we want to find the joint function. So we want to find the joint function, and that will be the likelihood function, which is the product of these marginals. So we have mu sigma squared, and the product, now we substitute the function, which is 2 pi sigma squared to the power minus 1 over 2. So this one, again, to avoid the question we had on Monday, this one is nothing but 1 over the square root of 2 pi sigma squared. So you can write this like that. And then we have e to the power minus 1 over 2 theta, 1 over 2 sigma squared, multiplied by xi minus mu squared. Now, what is the product of this? This one is a constant. It has nothing to do with the subscript I. So you multiply the constant n times, you get the constant to the power n. So we're going to have 2 pi sigma squared to the power minus n over 2. And what is the product of e to the power 1 over 2 sigma squared xi minus mu squared? So we are multiplying the functions of the same base. So we add the exponents. So in this case, we are going to have minus 1 over 2 sigma squared, the summation of xi minus mu squared, I ranging from 1 to n. So this is the likelihood function. This is the likelihood function. We can differentiate this if we know these rules of differentiation. So you can differentiate this and solve the results. Or we can take the natural logarithm and we differentiate the natural logarithm. So now the log of L of theta sigma squared is nothing but the log of this entire function or joint function, summation of xi minus mu squared. I'm not going to repeat the rules of logarithms. So now you know that the log of AB is nothing but the log of A plus the log of B, and the log of x squared is nothing but n the log of x. So I'm going to apply that to this. So this power will come down. We'll have n over 2, the log of 2 pi sigma squared. Now, plus the log of this guy. So the power will come down again. So this plus will become a negative because we have minus 1 over 2 there. So the plus will become negative because of that negative. So we'll have negative 1 over 2 sigma squared xi minus mu squared. Multiply by the log of e, but the log of e is 1. So it's not necessary to write the log of e since it's equal to 1. So now we have the natural logarithm of the likelihood function. We can differentiate the natural logarithm. First, if we want to find the estimator of, because we have 2 parameters. So if we want to find the estimator of mu, we are going to differentiate this likelihood, the log of the likelihood function with respect to mu. If we want to find the estimator of sigma squared, we're going to differentiate this with respect to sigma squared. So now let's start with mu. Let's find the estimator of the population mean. So we're going to differentiate with respect to mu, the log of the likelihood function. So it means sigma squared is a constant here because we are differentiating with respect to mu. So sigma squared becomes a constant. So when we differentiate this guy with respect to mu, you can see that there's no mu here, which means this guy is a constant and that is 0. So the derivative of this function with respect to mu is 0. Then we move to the second function, then we differentiate this. So you know the rules of differentiation. You differentiate the power first, then you differentiate the function. So when we differentiate the power, 2 will come down and we'll have minus 1 over 2 sigma squared multiplied by 2, summation of this minus mu. 2 minus 1 will give us 1. So we have to the power 1. We go inside and differentiate the inner function. The derivative of xi with respect to mu is 0, and the derivative of minus mu with respect to mu is -1. So we have -1. So this minus will take care of this minus, and these two will take care of these two. So now we are left with 1 over sigma squared summation of xi to the power n xi minus mu. So that's what we are having. That's what we are having. So again, we have to equate the partial, we have to equate the derivative to 0 and solve for the parameter. So we are going to equate the derivative of the natural logarithm of the likelihood function to 0, which imply that 1 minus sigma squared of xi minus mu is equal to 0. So that's what we get there.
Sir,
We want, yes?
how about 10 minutes break?
Can we please finish this, then we take a break, because it will not make sense to stop here and take a break. Let's just finish this one, because we are almost done. We are 2 steps away from the answer. So we'll take a break after this.
Okay.
Thank you. So we have this equated to 0. Remember, we differentiated with respect to mu. So sigma squared it's a constant. So we want mu to be subject of the formula. So we can multiply both sides by sigma squared to get rid of this constant, because we don't want it. So we multiply both sides by sigma squared. We have summation of xi minus mu, which is equal to 0. So you distribute the summation. We have summation of xi minus summation of mu, which is equal to 0. Now, mu is a constant. You add the constant n times, or you sum a constant n times, you get that constant multiplied by n. So we have n mu. We have n mu, which is equal to 0. And this implies that we can take this term to the right, and when we do that, we have summation of xi, which is equal to n mu. We solve for mu by dividing both sides by n. We have mu, which is equal to summation of xi over n, and this is equal to x bar. So now, what does this mean? This simply means that mu hat, which is the estimator of the population mean, is nothing but x bar, which is the sample mean. So we are taking the 10 minutes break. We'll resume at 12:10. Then we look at the estimator of the variance, because this is the estimator of the mean. Remember, the normal distribution has two parameters, which is the mean and the variance. So let's take a break.